door. This is standing at my front door looking out toward just a little bit of the walkway, so I enjoy doing this. Just to make sure, I sent Allie the update, but tomorrow morning there's going to be a cold breakfast between 8 and 10, so that means you can get up whenever you want and have breakfast, and be like bagels and yogurt and fruit and whatever. And then at 10, I think we agreed at 10 o'clock to meet here. Is that right? And then at 1 o'clock, I'll post a schedule before 1 o'clock tomorrow. We'll be doing almost 24-hour extractions for chlorophyll. And so in the labs this afternoon, you'll be collecting samples, filtering them, putting them in acetone, and then tomorrow read them on 2 different fluorometers. So I'll set up a schedule so that we don't back up too much. And then 3:30 to do the scattering report. And you are not going to have a whole lot of time tonight because Emmanuel has invited Laura Lindenfeld, who's a communications expert. But hopefully tomorrow during the day, you'll have time to work on the scattering report. And then 6 o'clock, there'll be a barbecue outside. And the fluorescence report will be Monday morning. So. Right. And then I had a comment saying that even though it's better for the recording to have the lights off, that it might not be better for you. Do you guys want the lights on or off? Who wants the lights? Okay, turn them on. Who wants the lights on during the lecture? One?
There is not much of a difference when you keep it constant.
Right. So is this okay with that light on? Okay. So we'll do that then. But just remember, feedback. If you're not happy, we'll raise the question and take a vote. So today I'm going to talk about fluorescence, and I cannot tell you how many people spell it flower instead of fluor. So please make an effort to spell it fluorescence instead of reversing the two. Just as Kurt was talking about somebody who is really annoyed at certain things. That's something that really annoys me. So these are examples of fluorescence in a test tube. This is chlorophyll with red light shining on it. And this is fluorescence in a diatom chain with the red. So if you come away with nothing today, the 3 things I'd like you to remember is that fluorescence is re-emission of absorbed light. So you should be thinking it's related to absorption, and that ties in with Colin's lecture. And that in the ocean, fluorescence has 3 major sources: CDOM, that Ken talked about, chlorophyll A, that I'll talk more about, and phycoerythrin, that I'm not going to really talk about. And these 2 are major. This one is typically minor, unless you have something like a big bloom of trichodesmium, which is nitrogen-fixing cyano. And then the 3rd point is that with some caveats, and you're starting to get the point that there's a lot of caveats in everything that you do in terms of making the measurements to try to get it and interpret it, is that fluorescence can be used to infer mass. And that could be concentration of CDOM, chlorophyll, or phycoerythrin. And the caveats, going back to the Mobley law of conservation of misery, is the caveats can be really, really critical and can be sometimes severe. So what fluoresces in the ocean? Here's chlorophyll A fluorescence. And if you remember from Colin's absorption lecture, chlorophyll A had 2 little harmonic peaks and then the major Q-band peak. Well, similarly, it has the major emission, and I should have put the 2 of them on the same slide. This is chlorophyll fluorescence with the second little peak. These kind of look like they're blurred together, but you can actually measure fluorescence out at 720 and about 740. So you have the same kind of mirror image harmonics. Phycoerythrin fluorescence, there's different flavors of phycoerythrin, like phycourobilin. That fluoresces in the orange. Here's an absorption spectra with an absorption peak in the yellow, and the fluorescence, the phycoerythrin fluorescence is shifted to the red wavelengths. And then Ken had talked about these excitation emission spectra that people use to characterize CDOM in terms of the excitation at multiple wavelengths and then the emission at multiple wavelengths. And they use those to interpret what might the composition be, use them to characterize differences in different water masses. And so typically you can't see chlorophyll fluorescence in remote sensing spectra, and remote sensing is more the next 2 weeks. CDOM, yes, somewhat. And usually you don't see any indication of phycoerythrin fluorescence unless it's being stimulated with something like LIDAR, a really bright light. But the 3 types of things in the ocean that fluoresce are chlorophyll, CDOM, and phycoerythrin. There are 2 types of measurements, and in this afternoon, you'll be looking at active fluorescence, and that means that the light source that stimulates the measurement is an artificial light source. And so similar to the types of sensors that you've used in the absorption and scattering lab with Emmanuel and Colin and Ollie, you'll be using an active artificial light source to stimulate fluorescence. And we're not going to do time-resolved femtosecond chemistry, but that's used a lot in understanding CDOM characteristics and understanding the picosecond photosynthetic processes. The second type is passive, and that's where the sun is the source of the energy. That's the source that's stimulating the fluorescence. And you're going to see that next week with the field radiometry, and you're going to see it in the hydrolite. And Ken and Kurt talked a little bit about that. Here's an example of reflectance spectra where you can see for low chlorophyll water, and so this is wavelengths from 400 to 800. Here's the chlorophyll peak, that's chlorophyll fluorescence. For higher chlorophyll water, you can see that much, much more strongly. And if you go deeper into the water where there's still enough light to be absorbed by chlorophyll, there is no red light at all, and the only red light is what you see from that re-emitted signal. And so that's pretty much what I'm going to say, with the exception of one slide, about passive fluorescence. And I'll spend the rest of the time talking about static fluorescence, active sensors. So what I want to do is cover what is fluorescence, the equation where fluorescence is a function of the absorption coefficient, the excitation energy of the light source, and the quantum yield of fluorescence. And so the fluorescence output is a function of these 3 terms, and I'll go through them piece by piece. And then I want to just talk a little bit about some ecological insight using fluorescence. And again, with that caveat in terms of how you get from fluorescence to mass. So Sir Gabriel Stokes was the one who coined the word fluorescence, and he derived it from fluorospar, which he derived from the name of a mineral. And this is not quite as cool a picture as Ken had, but by shining UV light on it, he could see light emitted, re-emitted by feldspar. And he noticed that the visible light, he noticed that when he exposed this to UV, he saw emission, because we can't see visible light, UV light. So it has to be, if he was going to see it, it has to be in the visible. So he exposed a mineral to UV light, and then he could see visible light. And so it's named after him in terms of, here's the absorption spectra, that's a cartoon, and here's the emission spectra. So it's some fraction, and that gets to this term quantum yield. some fraction of the energy that's absorbed, and so it's got to be absorbed, is going to be re-emitted, and it will always be re-emitted at a longer wavelength, which means lower frequency and lower energy. And so if I knock this off the desk, it's always going to go downhill. Same thing for energy. So the emission is always going to be red-shifted, and that difference is the Stokes shift. The magnitude of the Stokes shift will be greater at longer wavelengths. And Colin had talked a lot about absorption in her lecture in terms of absorption from one electronic state to the next highest electronic state in terms of the orbital electronics. And the loss of energy of fluorescence is always from the lowest vibrational state at that higher electronic state down to the ground state. The main point is that if a photon, the energy of a photon is going to be absorbed, it has to be equal to the energy difference between the ground state and the next highest electronic state. Some of that energy will be lost as vibrational energy, so that would be heat, and some could be lost as a photon in terms of the re-emission of that energy as fluorescence. And so an important, and I'm just going to, this is on the web, you don't want to get into all of this. We're just going to be talking about one very simple transition between the various electronic states, and that's in this cartoon here. So an important point is the energy for absorption has to be equal to the energy required to move an electron from the ground state to another higher state. And the energy re-emitted as a photon will be equal to the energy from the lowest vibrational state of the S1 electronic state down to the ground state. So the summary is that emission will always be from the lowest vibrational state. It'll always be red-shifted, and it will be a mirror image of absorption. So here's an absorption spectra, here's an emission spectra, and typically there'll be a slight overlap. In terms of the design of a fluorometer, there's two things that are kind of in opposition. You want to have the highest possible excitation energy, because remember, fluorescence is directly proportional to the excitation energy, but you want to have a lack of spectral overlap between your excitation energy and the emitted fluorescence. And so how efficient do you think filters are in eliminating energy, excitation energy, so that the detector doesn't pick up any of that excitation energy, which would be recorded as a signal? You know, what do you think the efficiency is of blocking excitation energy? They're not that great. Maybe 10 to the 3, 10 to the 4th. So the higher the energy, because remember the fluorescence excitation, so fluorescence is going to be directly proportional to the excitation energy. So you want to maximize your signal, so you want this to be really bright, but then you're working against how good the filters are in terms of blocking any of that excitation light to get into your detector. And I'm going to come back to this in terms of why chlorophyll is so beautiful. And you should be thinking about the absorption spectra of chlorophyll. So just in terms of the reality of what we have to deal with. So here's where I thought I had this. So here's the absorption spectrum of chlorophyll. This is an acetone. And so if you follow this line, that's the absorption spectra, and here's the fluorescence emission spectra. And so here's why chlorophyll is so beautiful. You can excite this, and if you remember Colin's lecture, in the Sorey peak, the energy goes to the second electronic state. It's emitted as heat to the first electronic state, and then it can be refluoresced, re-emitted as a photon. And so you can have a very strong excitation, have a really good set of filters, and be able to maximize your signal in terms of the red fluorescence. And so in the ocean, we're able to have very high excitation energy because of this ability to have a big opportunity to block that excitation energy from bleeding over into the detector. And because fluorescence is emitted isotropically, which means that it's emitted in all directions, we can take advantage of that by doing what? In terms of, you're going to build you're probably going to build a fluorometer with the Arduino boards.
I don't know here, but yeah.
Right. So if this is the light source, and this is your cell or your sample, where are you going to put your detector? 90 degrees. So the spectrophotometer, you're passing the light straight through the sample because you're looking at the absorption. With the fluorometer, light is being re-emitted in all directions. So if you have a filter that's, say, 10 to the minus fourth blocking the excitation light, if you now collect your light at a right angle to the sample because it's being emitted in all directions, you can knock down a lot more of the stray light. And so you don't have to just strictly depend upon how good your filters are. So chlorophyll is great because there's this wide separation spectrally between the excitation and the emission. And then all fluorometers are set up to collect at right angles. So here's your light source. Usually you have an excitation filter. And so the idea is that you pass blue light through to the sample, light's emitted in all directions, and then you collect at 90 degrees light that then passes through a filter. This blocks out red light, this blocks out blue light. And then ideally, you're only left with the light that's been emitted by your sample. So just kind of a little bit about how you take advantage of that in terms of setting up the fluorometer. So now I'd like to go into this equation and look at each part of this and see how that affects the fluorescence. And this involves some of the caveats in terms of how do you get phytoplankton? You know, so the basis is we want to get at phytoplankton biomass. If you believe, and I'm not saying you should, if you believe that chlorophyll has some relationship to phytoplankton mass, and that phytoplankton mass, we've been saying that the currency in the ocean is to a large degree carbon. And if you go back to my lecture on Tuesday, I talked about this carbon to chlorophyll ratio and the fact that the carbon to chlorophyll ratio can vary by maybe a factor of 4. You know, so you've already got that in your mind in terms of this variability. So if we say that, you know, within some constraints, chlorophyll is related to biomass, how is chlorophyll fluorescence related to chlorophyll? So let's go through some of this. Okay, so here's the equation. The analogy is for Beer's law, absorbance equals concentration times the molar absorptivity of the material. So that's just how much light per mole is absorbed, and the path length. And so if you hold the molar absorptivity constant, like the chlorophyll concentration in 90% acetone, you hold the path length constant, the absorbance is directly related to the concentration. And you can have something that looks like absorbance is a linear function of concentration. And so that's what chemists do all the time. You go to the doctor, they take your blood, they send it off to a lab, and they measure some test, and they're holding this constant and that constant, and the absorbance is equal to the concentration of something in your blood. For fluorescence, what is typically done in a fluorometer is this is held constant, and you hope that this is constant so that this is equal to the absorption coefficient. And very often what we do in the fluorometer is we actually say, okay, the absorption coefficient and the concentration are really similar. I'm just going to replace that and say that the fluorescence is equal to the concentration. And I'll show you in the lab this afternoon how we calibrate our fluorometers. And that's what we're doing, is we're saying that we're going to put in a certain concentration and we'll measure fluorescence. But the physics is it's the absorption coefficient. So A is absorption coefficient with units of reciprocal meters, just like in the labs this week. It's related to the concentration. E is the energy of the excitation, lambda is the wavelength, and the quantum yield of fluorescence is the moles of photons emitted over the moles of photon absorbed. And just hold this till I talk about photoprotective pigments and how that kind of, you have to keep that in mind. So,
is that kind of like efficiency?
Right, efficiency. Some people call it quantum efficiency, some people call it quantum yield, but it's moles emitted over moles absorbed by that energy. Okay, and so again, just remember, fluorescence is directly proportional, if everything else is held constant, to energy, or directly proportional if everything else is held constant to that.
Does that quantum yield of fluorescence change for species?
We're going to get there. That's part of the Mobley conservation of misery. I like that. You can probably tell. Okay, so we're talking, I'll put the little key up here, what we're talking about. So absorption coefficient. So in terms of calibrating, here's, and I forgot that I had it right here, here's the chlorophyll concentration in acetone. And so there are 10 concentrations, micrograms per liter. And here's the fluorescence in relative units that we measured on our fluorometer. So we just do a calibration curve, and we come up with our calibration equation, and we use that for 6 months or so. The one thing that you got to look out for is that, have you ever had an incandescent lamp and about a year later you go, this room is really dark? And so the lights age, and it looks something like this. If this is time and this is the energy of output, is you have a really fast burnout, and then there'll be a slow gradual decline. And so you have to make sure you know that this isn't changing. The standards are about $200. It takes a little bit of time to do that. And so every 6 months to a year, depending upon the usage, you should buy standards and calibrate your fluorometer. But there is a way to track it, because everything is dependent on this being constant, is we have a secondary standard. And so when you go in the lab today, in the log sheet, we'll measure the chlorophyll concentration tomorrow. There's a column for temperature, and there's a column for secondary standard. the secondary standard is a piece of plastic that's embedded in a tube that you stick into the fluorometer. And so it just helps you track. It doesn't, you don't want to use that as a calibration, but if it starts changing, you go, aha, I need to go and do this because I think this has happened or something else has happened. The other thing is temperature. There is a negative coefficient of fluorescence as a function of temperature. And so if the temperature increases, there is more quenching by interaction. So what happens when you increase the temperature, you have more interaction with molecules, and so you have more opportunity to have radiationless decay. That means not fluorescence. So you have more of that energy is dissipated as heat. So the higher the temperature, the less fluorescence you have. And I remember going to a talk at an ASLO meeting, and there was somebody from Mississippi who showed this curve of his calibration standard, and it went like this, and it was directly related to the room temperature because in the summer they cranked up the air conditioning, and so it was lower temperature. And I remember at a meeting he talked about this in terms of, you know, this annual oscillation of his calibration, and it's like, dude, it's temperature. So we've got a thermometer there. If you go to, so say you calibrate your fluorometer at a 20 C room, and you go to the tropics, and they don't have really great, okay, Dot, what's the temperature when you go in Vietnam? When you go out on a boat, what's the air temperature on your boat when you go sampling?
This is depend on the season.
Yeah, summertime.
This is summertime. This is about 25 to 30.
Okay, 25 to 30, but your lab was 20.
No, the lab is around 40.
40, okay, even better. So you calibrate, right, okay. So you calibrate your fluorometer at 40 degrees, and now you go out, and the temperature is 25 degrees. So you're going to have more fluorescence out of that sample at 25 degrees than you did in your laboratory. So you got to make sure that you're really close to that same temperature. It's a minus 0.3% per degree C for chlorophyll, chlorophyll and acetone. But anyway, just pay attention to temperature. And this goes for a lot of calibrations as well. At really, really high concentrations, usually you go off scale because the manufacturer doesn't trust scientists. But if you get to really high concentrations, you'll start getting to something that's called the inner filter effect. And so you will have self-absorption. If it's too concentrated, more light will be absorbed. Again, it's thinking about a packaging, but a packaging in a tube. You can get into a nonlinearity at high concentrations. I think for most benchtop instruments, that's not a problem. But one of the things I want you to think about this afternoon in the lab with a manual is whether you could get up to a problem of nonlinearity with that benchtop model. For those of you who go to Chesapeake Bay, Colin?
Yeah, when you're calibrating your fluorometers, every fluorometer you should test and find out where that nonlinearity is, because the instruments will report 4,000 digital counts, but the signal that you're getting at 2,000 digital counts might be outside the linearity. So just because your sensor has a very broad range doesn't mean that's actually usable.
So you'll get a chance to explore that this afternoon. In terms of the relationship between fluorescence and absorption, I never know whether my X and Y in this case should have been switched, but this is fluorescence per cell in living cells. So this is what we call in vivo. So that in vivo is in life. So in vivo fluorescence versus absorption at 488 for cultures. And you notice there's considerable scatter, particularly for the larger cells, but the fluorescence of chlorophyll per cell was related to the absorption per cell. And keep this figure in your mind when we go to one of the next slides. And this was measured in a flow cytometer. And then we measured absorption at 488 in a spectrophotometer. But pigment packaging can affect the fluorescence. So if we were doing this in typical fluorometers at really low excitation energy, what we would see is a variability in the fluorescence to extracted chlorophyll as a function of pigment packaging. Now, pigment packaging can change as a function of size. So if you have a little cell with the same concentration per volume as a big cell with the same chlorophyll concentration per volume, there'll be more light absorbed, there'll be less light absorbed normalized to chlorophyll because some of the chlorophyll molecules are not seeing the light. The first chlorophyll molecule absorbs the light, so the second one is not seeing as much light, so you have less absorption normalized to chlorophyll. So this is from Morel and Bracot. So if you have less absorption per chlorophyll, what do you think your fluorescence per chlorophyll is going to look like? Yeah, so you're going to see a similar type of relationship. And so that could be due to cell size, or it could be due to photoadaptation. Cells that are grown at low light are going to have more chlorophyll per cell than cells grown at high light. So you can get packaging from two things. So let's look at some real data. So this was data from San Francisco Bay by Alpine and Klern. This is an old paper, 1985. The citation is down here. You have it on the web. And so what they did is they separated phytoplankton using a sieve. And they had what they called net phytoplankton, and this goes back to Ivana's lecture about size. So they had net phytoplankton, and then they had what they called nanophytoplankton, so that's 5 to about 20. And then they had what they called ultraphytoplankton. So they have big to small. And what they found, the relationship between chlorophyll concentration, and that's extracted, like you're going to do this afternoon, and the fluorescence, and these are relative units, is they found that there was a linear relationship, more or less, between fluorescence and chlorophyll for all three of the size groups, but the slope was very different. And so the slope for the little cells was the highest, so there's more chlorophyll fluorescence per chlorophyll for the tiny things. For the intermediate cells, there was a little bit less fluorescence per chlorophyll, and for the big cells, there was even less. And so this is a classic study showing the effect of size-based pigment packaging on fluorescence per chlorophyll. So here's one of your caveats.